Hello, this is Jin from Dongguk University, third year student, major in semiconductor. For today, I will present my design for a 1024-bit SRAM system. The most defining feature of this SRAM is that it implements a 70-cell structure that cuts off the internal feedback latch, rather than using the conventional 60 structure. Using this mechanism, the latch feedback is temporarily interrupted during a write operation, making it more easier to override data and significantly improving the write margin. Furthermore, I adopted a VDD over 2 pre-charge scheme instead of standard VDD. This completely prevents a pre-charge disturbance, the unwanted flipping of cell data during a read operation. Because this scheme drastically enhances cell stability, we are able to minimize the overall layout area by designing every single MOS transistor as its absolute minimum size. The entire system is composed of peripheral blocks, row and column decoders, a cell array, and an ETDFF. Now let's look at the schematic. On the far left, the left circuit selects the decoder and syncs them with this clock. Here you can see four decoders, the peripheral block, and the cell array. During a write, data goes up through the up drivers into the cell. For a read, the bit line flip to the VDD over 2, pass through the buffers, and enter the ETDFF to match the clock perfectly. Below, this main section has same on as well, and the exact same 2056-bit structure is repeated 3 more times to complete our 1024-bit system. Next, let me explain the 1024-bit cell array architecture. Controlling 16 bits with a single elongated decoder using the PLD approach would drastically increase the parasitic capacitance of the lines, leading to severe and unacceptable delays. To avoid this performance bottleneck, I partitioned the 1024-bit structure into 4 separate 256-bit cell arrays and split the decoders into 2 pairs for both the horizontal and vertical axis. I'll explain how this routine works using the example of the 16-4-bit cell array shown on the slide. Here, we have 4 16-bit sub-arrays along with the 2 horizontal and 2 vertical decoders. With this arrangement, activating the decoders will inevitably select a line in two of the 4 sub-arrays at the same time. To prevent unwanted data conflicts, the unselected addresses in those activated arrays are designated as dead cells, which always point to 0. Let's see how the SRAM actually operates. If you look at the ping label number 2, this represents the case where B0 and C1 are selected. By activating decoders B and C, the unselected decoders A and D automatically point to 0, targeting the dead cells. At this moment, by enabling only the B0 switch that connects the bit line to the peripheral block, we can successfully isolate and assess the data as if only the single cell B0C1 were selected. The same logic applies to examples number 3. Well, let's look at the timing control, which is the most critical part of the SRAM design. In an SRAM, if the input data fluctuates while the word line is still arrested, incorrect values will be written into the cell. Therefore, we must secure a timing margin where the input data is held stable until the word line safely turns off. I synchronize the word line decoder inputs with the clock signal. That ensures that as long as the right signal is held for one clock cycle, the input value remains stable. When the word line drops, allowing for a highly reliable write operation. A powerful output driver inside the peripheral block strongly derives these values into the cell. During a read operation, the precise sequence of the pre-charge and word line timing is vital, because any overlapping or misalignment can corrupt the cell data. To handle this, the pre-charge enable signal is fully linked to the clock. When the clock is 0, the pre-charge turns on to set and float the bit line at VD over 2. When the clock transitions to 1, the pre-charge turns off and the word line turns on after a slightly international delay. This safely opens the cell without data flipping. The subtle voltage change on the bit line is then restored to a solid high or low level through the buffer into the first floor block. Finally, the data passes through the ETDFF at the output stage, where the signals are perfectly aligned with the clock edges for a clean final output. Next, let's look at the simulation results. Finally, we wrote the 1010 pattern into a 32-bit block. During the read operation, you can see that the pre-charge works perfectly when the clock is 0. Then the read value successfully comes out when the clock is 1. You can also see that the word line turns on exactly when the clock is 1. At this time, the read data goes into the ETDFF and we get the exact 1010 data we initially wrote. Finally, let's move on to the layout. On the left side, we have the circuits that control the decoder inputs. Next to them are the decoders, the peripheral block, and the cell array. Let's zoom in for a closer look. Here's the decoder section right next to its peripheral block, and on the right side of that is the core cell array. Moving further along, the section on the far down is where the ETDFF is located. We check if the physical layout was done perfectly according to our schematic. The LVS check passed successfully, which means the layout matches our schematic 100%. For the DRC check, we cleared all critical rules with zero errors, except for boundary and density rules, which were not required for this project. In short, everything from the schematic design to the final layout verification works very cleanly and stable. Thank you.